Welcome to The Explainer. Today, we're diving into a genuinely profound human problem in medical science, and more importantly, the microscopic tech that's poised to absolutely solve it. We all rely on modern medicine, but the actual pipeline for creating those life-saving drugs, well, it's kind of fundamentally broken. Okay, let's jump right into this. 90%. That is the staggering failure rate of new drugs once they hit human clinical trials. Just think about that for a second. For every 10 drugs that scientists are confident enough to test in humans, 9 of them are going to fail. And those failures, they carry an unimaginable financial weight. It literally costs over $2 billion to bring a single new drug to market. The whole process is incredibly long, wildly inefficient, and get this, human liver toxicity is the single most common cause for these massively expensive failures. Clearly, the traditional ways we test things just aren't cutting it anymore. Section 1. Enter the organ on a chip, a revolutionary solution. So, the grand reveal to this whole pipeline problem is the organ on a chip, or if you want to get technical, microphysiological systems. Basically, these are microengineered devices that use real human cells to perfectly mimic the structure and function of our actual organs. From the heart and brain all the way to the lungs and gut, we can now literally recreate human physiology outside the human body. How wild is that? Now, there's a pretty stark contrast between those old traditional testing methods and this new frontier. While animals like mice or dogs do give us broad data, their systems just aren't human. A rodent's respiratory system is vastly different from ours, right? But these chips, they accurately simulate actual human mechanics. The lung on a chip, for example, uses a tiny membrane that physically stretches to simulate a real, breathing human lung. Section 2, the engineering behind the biology. Microscopic manufacturing. Now you might be wondering, how exactly do you build a microscopic home for human cells? Like, how do you create an environment that actually tricks these cells into behaving exactly as they would inside your own body? Well, it actually starts by borrowing heavily from the computer chip industry. Engineers use these super intricate BioMEMS techniques. That stands for biological microelectromechanical systems. We're talking about lithographic pattern transfer, precise wet etching of glass, and high-heat thermal bonding at like 600 degrees Celsius just to create these nanometer-scale structures. They're even moving from flexible silicone-like polymers like PDMS straight into advanced multi-material 3D bioprinting. By meticulously layering those materials, glass and flexible polymers, engineers can create these dynamic microfluidic channels. Honestly, it's mind-blowing to think we're out here building microscopic blood vessels out of glass and polymer. Fluids loaded with nutrients and drugs can flow continuously through these tiny spaces, totally mimicking the exact shear stress and flow of blood moving through human vessels. Section 3. The liver chip proof. Revolutionizing safety. As we touched on earlier, human liver toxicity is just a massive hurdle. Drug-induced liver injury, or DILI, actually accounts for 13% of all acute liver failures in the US. When a liver fails to properly clear a drug, you get chemical stress, mitochondrial impairment, and ultimately cell death. Not good. But check out how the liver chip tackles this. By sandwiching real primary human hepatocytes, along with other essential cells like endothelial and Kupffer cells, inside these chips, scientists perfectly recreate the complex 3D microenvironment of the human liver. Instead of just growing flat cells in a static petri dish, it's an actual living, breathing cross-section of human tissue reacting in real time. So here's the so what of it all, the hard data. Liver chips correctly predict toxicity 80% of the time, and amazingly, with absolutely zero false positives. Compare that to live animals, which sit at around 70%, or those traditional static 3D spheroids that only caught toxicity 42% of the time. The liver chip undeniably completely outperforms the conventional models we've relied on for decades. And because of this unmatched accuracy, running drug candidates through a liver chip early in the lead optimization phase changes the whole game. It acts like a super-powered filter, catching those toxic signals before they ever reach human patients. This ensures that only the absolute highest quality, safest drugs even make it into clinical trials. Section 4. The future. Body on a chip. The ultimate sequel. Okay, we are now entering the era of the body on a chip. Instead of just looking at a lung or a liver in total isolation, Scientists are physically linking multiple microorgans together, using those fluidic channels to simulate complex systemic responses across the entire human body. Just imagine the real-world application here. Say you swallow a pill, the oral drug is absorbed by an intestine chip, the fluid then transfers over to be metabolized by a liver chip, and finally, it's cleared by a kidney chip. This linked-up process lets researchers spot hidden secondary toxicities. Like, what if a drug is broken down fine by the liver, but the resulting metabolite ends up being totally toxic to the kidneys? Now we can actually see that before it ever reaches a human. And this isn't just some theoretical sci-fi concept, it's a regulatory reality right now. Supported by recent legislation like the FDA Modernization Act 2.0, this technology is actively moving us toward a future in pharmacology that relies way less on animal testing, drastically de-risks drug development, and operates with just incredible precision. Which leaves us with a pretty thrilling look ahead. With the integration of AI for real-time analysis and the ability to actually seed these chips with a specific patient's own stem cells, you really have to wonder, how soon will a personalized body on a chip dictate the exact medical treatments you receive? Imagine testing a cure on a microscopic version of your own body before you ever take a single pill. That is the true promise of organ-on-a-chip technology. Thanks for joining me on this explainer, and keep questioning the future.